I was told I should record myself, as I usually do. I suppose there is no harm. Actually, I was threatened with being recorded by some experimental technology that tracks the lecturer. Let me just close the door.
What happened?
It did not materialize. It's fine by me. So I've been fighting an English bug for the last 10 days or so, and I think I'm okay. We'll see. So this is now going to be the second part of the course, which to some may seem unrelated, somewhat unrelated, but I hope we can make strong connections. Maybe not so much at the level of formal mathematics, although it would be possible, but a lot of work. But certainly at the level of ideas, you should be able to see that we're essentially doing the same thing again, but with a different kind of formalism. And it is always good to see the same subject from two different points of view. That is always going to be a fruitful exercise. So the second part is going to be about homotopy type theory, which is a particular kind of type theory. Type theory is a formalism, a logical formalism, that was developed several times by several people, starting with Bertrand Russell. It was his attempt to avoid paradoxes of set theory. And then later on, so it was quite complicated. So set theory became a preferred alternative. And then later on, Alonzo Church gave his own version of what is now called simple type theory, which can serve also as a foundation of mathematics, and it is in fact implemented in some proof assistants nowadays, the HOL family of proof assistants. And then in the early 70s, Martin Löf gave his own version of type theory, which was supposed to capture a constructive understanding of mathematics, as in constructivism, Browerian constructivism. No? Doesn't want to come in? Okay. And it is this formalism that we are going to use, but it is going to be extended with recent developments that started roughly around 2006 probably. By 2009 it was already clear that there's something there, very much so, and then in 2012 there was a special year in Princeton as the Institute for Advanced Study where homotopy type theory got properly developed. And there is a thick book that is freely available that you can have a look at, which shows how much you can do. And you will see in there things like the Hopf vibration, which has later on been worked out much more elegantly. So, but things like the Hopf vibration, Blaker's masses theorem, fundamental groups of various spaces, category theory, set theory, real numbers, everything is in there. So what we're going to be looking at is a foundational theory, which means a mathematical theory which aims to be so general that you can do a lot of mathematics in it. In particular, you don't need any logic in set theory. It's going to be just type theory and nothing else. Okay, so no logic, no set theory. In fact, we are going to see later on that logic and set theory are incorporated into type theory as two levels of the mathematical universe, and these are the two levels that have particularly simple homotopy theoretic nature. So you can sort of reverse things and start all of mathematics with an expanded view of the universe, mathematical universe, where the mathematical universe does not consist of sets at first. At first, it consists of a much richer geometric kind of objects, some of which are sets. So I know that this is all a bit weird and strange because of your upbringing, because you were told that sets are fundamental. So this is going to be an exercise in clearing your mind, forgetting what you already know. At the same time, you should not forget everything that you know. You should just forget the formalism. All of the mathematics is still there. Your idea of a circle existed way before you came to this university. And when you were a little kid, you didn't have any problem with the circle, even though you didn't know any set theory. So the circle was there as an idea. And in fact, if you work professionally in any kind of mathematical branch, after you have mastered the subject, you will very likely view and consider the objects that you study as being kind of independent of any particular formalism that may be popular in the given century that you live in. After all, differential equations were solved before Dedekind constructed real numbers, right? And geometry existed a long time before most of foundations of mathematics. So history teaches us that viewing mathematics as being built on top of logic is just one option. It doesn't have to be. And we are not going to follow that. We're going to start holistically with something else. Okay? And this is the topic of the first lecture, which is type theory. So today, we're going to look at the fundamentals of type theory, in particular Martin-Löf type theory. We will not be able today yet to construct anything interesting like a circle or a double cover. You'll have to wait a little bit until we get to that point. But when we do, we are going to see how to construct circles and double covers and spheres and suspensions and things like that directly on top of a formalism without having to spend 3 years in school during which you learn real analysis 1, so first of all arithmetic, integers, rationals, real numbers, basics of metric spaces and topology, Euclidean topology, the notion of a continuous map, the notion of a path as a continuous map. Okay, so all of these things you need to know before you can speak about the homotopy of a circle. We're not going to take that route. We're just going to start with type theory, and we're going to have direct ways of constructing objects of interest. So I think this is very interesting. Of course, the question is going to be how advanced is it? As I already said, simple things like Hopf vibration can be done very nicely. Fundamental groups can be computed. But given that the subject is now 7 years old properly, it is maybe not surprising that it's not, we cannot reach for unsolved problems in abstract homotopy theory. Nevertheless, it seems to be clear that this is a useful formalism that in the future may be a useful tool that may be able to good for solving certain problems. For us here, I think the important thing is to expand your horizon and see how you can view things in more than one way and how you can do mathematics in more than one way. So anyway, let me get to the topic of lecture 1, which is going to be type theory. And by the way, I've taken it upon myself to write lecture notes, which are 75% complete for this lecture. And I will very much try to keep up. I will try to avoid writing a book, because that I cannot do, but short notes I think should be useful together with whatever I'm writing here. And these will be found on GitHub. There's a GitHub repo, and they will be collected there. Okay, so as I already mentioned, type theory is a foundational theory. So we need to scratch what we know, a little bit of what we know about logic and set theory, and you should think of what I'm going to present to you as a kind of just a new mathematical theory, as if you've never been to a geometry class and then suddenly somebody starts talking about points and lines. And of course, you know about points and lines from the kindergarten, but here there will be given very precise rules about points and lines and what you can do about them. That's the difference. So we are definitely going to draw on our mathematical intuitions, but we will be careful to give rules of what's going on without relying on existing formalisms as much as possible. Having said that, of course, I need to be able to rely on certain things. For instance, I need to know that you are familiar with how syntax is written, of course, right? I cannot start explaining today how to write the letter A. That is something that you need to understand. You need to understand the notion of a symbolic expression and so on, because that's the formalism I will use. So I need to start somewhere, and I take the right to start at whatever level I deem appropriate. But if you're interested in details, trust me, I can go into more details that you want to hear, but offline. So if you would like to hear about more details, then please come to me and I will make you use proof assistance, and then you will know all the details because the computer will check for you that you didn't miss any. It is also a very useful exercise. However, these lectures are specifically targeted at mathematics. We are staying well clear of any computer science here. Okay? So this is specifically targeted at mathematicians. So for instance, I will not tell you much about, I will try to sweep as much formalism under the rug as I can, because that is typically something that annoys normal mathematicians. Okay, so what is type theory? I have been asked to lecture on the basics of type theory, and I always wondered, is there a single phrase to explain what type theory is? And I think there is a good phrase. And the phrase is that this is a theory of constructions. It's a mathematical theory of constructions. Theory of constructions. Now, what does that mean? If you look at mathematical practice, I think there is no doubt that there are several important activities in mathematics. One of them is constructing various kinds of objects. In geometry, if you look at Euclid's Elements, do you know what the first proposition of the first book of Euclid's Elements is? It is not a statement of fact. It says, wait, I have it written here, in English, to construct an equilateral triangle on a given finite straight line. That's what mathematics begins with. How do you get an equilateral triangle on a straight line? It is not the statement that such a triangle exists. It does not ask you to prove that it exists. It literally asks for a way of constructing such a triangle. So constructions are an important aspect of mathematics. It is not the only aspect. Of course, in mathematics we also make statements of truth, such as, for instance, that 2 points in a given construction coincide, or that 2 lines are perpendicular or parallel. Those are statements of fact. Nevertheless, also a proof itself, a mathematical proof, is a kind of construction. After all, you proceed from basic axioms and you build your argument using rules of logical inference, and that is a kind of construction. It is no different than constructing, say, some element of a ring using some basic elements and operations. So also a proof can be seen as a construction. So it should be possible to start to take in mathematics as the basic notion that of a construction rather than statement of fact. Logic is about statements of fact. Logic is about making statements of what is true and what is false, right? And that's how logic builds foundation of mathematics. You speak about what is the case. When we want to construct things, then it's going to be a different story. We're going to give rules for making things, rules of construction. But not only rules of construction, we also have to give rules of deconstruction. Because if we only ever just construct things, that is going to be extremely boring. The other important part is that when you have a mathematical object, you can take it apart. If you have an ordered pair, you get to see its first component. If you have a number, a natural number, you get to test whether it's a zero or successor and then do something depend on that. If you have a function, you may apply it. So there are always ways to use mathematical constructions or deconstruct them. So it's not going to be just constructions. Okay? So that's what we are trying to get to. There is a little more background here on how things are set up in the notes, with a little more philosophy, and you may be interested to read this. But I would like to proceed, because I'm trying to cover some ground here, directly to the more mathematical bits. So what we're going to say is that we're going to have, okay, so let's draw a triangle. Let's see if I can draw a triangle with my bare hands. Here? Sure. There we go. Who can say it's not equilateral? Okay, so in type theory, there are now, I have to, since there's no logic and no sets, I have to say what there is, okay? So there, whenever you have a kind of construction, it's always of a certain, we're going to say it's of a certain type. Constructions are not just arbitrary actions that you perform. It's not interpretive dance on, on the stage where you just sort of do whatever you like. I'm sure that if any interpretive dancers are listening to this video, they are going to be very angry with me. But the point is that there are strict rules. Mathematics is more like classical dancing. So there are strict rules as to what you're supposed to be doing. And there are kinds of rules. If I say that I'm constructing a point in the product space A cross B, then presumably I need to produce an ordered pair, and there's some sense to that. If I'm making a natural number, there are certain rules to be followed, like 0 is a natural number. If n is a number, then the successor is also a number. These are rules of construction. And they come in packages. And these packages are called types. So a type, we're going to have types. A type is like a package that describes, it describes a kind of construction that can be made. A kind of construction. Here you should understand construction in the most general, abstract sense possible. I'm not saying that I'm constructing strings or symbols or some finite objects. These could be real numbers, these could be elements of a Banach space, they could be homotopy types, it could be anything. But nonetheless, there are always some rules involved in how you make them. So it describes a kind of construction. We're going to see lots of examples. Let me just introduce the basic vocabulary. Now, when you construct something, what do you get? Well, the thing you get is some sort of a mathematical object. We have to pick a name. So the name is, we're going to call it an element or a point. And I'm going to stick almost exclusively with a point, but I'm telling you that many people call it element. Okay? Is the result of a construction. And when you make a point, when you create one, then you always follow a particular set of rules for a given type. Therefore, a point is always made according to the rules for a given type, and so it always have an associated type. The type, so if I have a point, say I have a point t, it always comes with a type. And we call this, we say that this is point t of type A. What we claim that here is, what this information gives us is that it tells us t was constructed in such a way that it follows the structure of the type A. Okay, so A reveals the structure of T. If I say that something has the type of a number, of a natural number, that tells you what kind of an object it is. If I tell you that something is a real continuous function from the closed interval to the real numbers, that's its type, that tells you something about what you can do with it, what kind of an object it is. It says something useful about the structure. Yes?
So, point is this object together with the type?
No, so a point...
Different types?
No. So that's a very good question. So the question is, can a point have different types? The answer is no. A point always has an associated type because a point is always constructed according to the rules of some type. And so when you use those rules, it automatically lands in that type. And each type will always give us different ways of constructing. It will never happen that you have two different types that overlap in any way. Okay?
So we can imagine that we keep track of constructions to use.
Yes. So we keep track of how the point is constructed. In particular, we keep track of the type. We always know where it resides. Now there is a geometric point of view here. I will make lots of analogies with geometric point of view. In fact, I will motivate all of this with a homotopy theoretic picture. What we are saying now is that a point always resides in a space, and it never resides in two spaces at the same time. Now, this second statement is a little harder to swallow, because you would think maybe if I have a point on the plane, it's also a point on some line in that same plane, right? But this is not how we're going to do things. There are very good and foundational reasons why we're not going to do that. And the one that is relevant to us is that we are going to make sure that all of type theory is homotopy invariant. We are not going to allow ourselves any form of expression that isn't homotopy invariant. This is a very severe restriction. In particular, this restriction means I should not be able to say things which can be broken by passing to something else that is homotopy invariant. Or, let me put it in a different way. A construction should be such that if I change its building parts with some other building parts which are homotopy equivalent, then the result should be homotopy equivalent. So, say, whatever I do with an interval of 0, 1, I should be able to do with interval 0, 2, accordingly, analogously, and so on. And so a lot of the restrictions we're making are in place so that this principle doesn't get broken.
Are types universal or maximal in some sense?
What do you mean? Give me an example.
Following your example of point belonging to a plane or
Yeah.
free space includes this plane, is there maximum principle somewhere here?
So that a point, there's some sort of a maximal space that the point resides in? No. A point resides, what space a point resides in depends entirely on how it was constructed. It was constructed by means of certain moves, certain things that you did, which determine what space you landed in. Right. So, for instance, if you said, let this point be, the intersection of these two straight lines in the plane, well, yes, then it's going to be in the plane because that's what you said, right? And we are going to be able to deal with the fact that maybe you want a point to be in two spaces at the same time. Of course, there are ways of doing that, and we're going to discuss them. Okay, but a priori, each space stands on its own, and there are points in it. And if you want to get a point from one space to another, you will need to be able to transfer it explicitly. It will not just be there by accident in the other space. So we have types. Think of them as spaces. We have elements. Think of them as points. Let me spend a little bit let me say a little bit about this notion of element. Why do we call it an element? Let us distinguish between a type of construction and the extension of a type. Now, the extension is something that is more general, comes up in philosophy and logic, and it can be applied not just to types, but also to concepts. And since we haven't done any type theory right now, I can't write things down. Let me show you how it works with concepts. The extension of a type, you can think of this as the collection, and I'm going to put collection in quotes here because it's meant informally, the collection of points of the type. Okay? It is important that we emphasize here that we are not saying that a type is a collection of anything. A type is a set of rules that describe certain kinds of constructions and their structure. It is about the structure of its elements. It's not about which elements, what is the extension of them. So to give you an example, you can have two things which are different but have the same extension. So for instance, here's a silly one. If you take prime, take even primes larger than 3 and lines in the plane, that are perpendicular to themselves. You're mathematicians. You thrive on pathology. You have no right to complain about pathology. So, these are two concepts which have the same extension. Namely, both extensions are empty. There is no prime larger than 3, and there is no line, straight line, which is perpendicular to itself. So these have the same extension, but clearly these are not the same concept. It would be ridiculous to claim that both these lines describe the same concept. So concepts, different concepts may have the same extension. Bertrand Russell's favorite example is the morning star and the evening star. So that's an example of different concepts that have the same extension. Both of them signify the same object in the universe, also known as the planet Venus. And so that's another example. So types are more like descriptions of structure. They are not like collections of things. Even though to every type we may associate the collection of things that it describes. However, let us be careful, because there is more to a type than just its collection. Because once we know how to write this down in type theory, we are going to have at our hands two different types, both of which have no elements, no points.
Can a type be a point? Can a type be a point?
Can a type be a point? That is a good question. And the answer is, well, if it is to be a point, it must be of a certain type. So you're asking, is there a type of types? Yes, we are going to introduce a type of types, and we're going to call it a universe. And that is going to be an interesting thing where we step out of the classical homotopy theory, because it poses the following question to homotopy theory. What is the space of all, what is the homotopy type of all homotopy types? And that is not a traditional question to be answered in homotopy theory. Nevertheless, we will see that this is an immensely useful concept, and we're going to do lots with it. It's the basis for Voevodsky's univalence axiom. Okay, let us go on. So we have points, we have types. That's not all. We are also going to, because you see, we're going to be able to build points and take them apart, maybe like project things, look, consider cases, apply functions and so on. We will be able to manipulate these, and it just so happens that sometimes a series of steps that you make results in the same kind of object, then a different other series of steps. So, for instance, if it may happen that, just if you have an ordered pair, I can take it apart, I get its first and second component, then I put it back together. Well, did I get the same ordered pair? Presumably. So the next step that we need is that we need to be able to observe something about these constructions, because if we never observe anything, it's all going to be very boring. It would be quite mystic and transcendental, right? You would just constantly think about the fact that you can make things, So it's a bit weird. So we need something, and we're going to follow algebra here. So in algebra, you make things. You have operations. You have plus and times and minus. They allow you to make polynomials and elements of rings and matrices. But that's only half of algebra. The other half is equations. And so we need equations. So we are also going to have equations. And equations, we're going to have two kinds of equations. One is we're going to be able to state the 2 points are equal. So the 2 points are equal. They must necessarily be of the same type. Otherwise, this is a nonsensical statement. You only get to compare points in the same space. If they're not in the same space and you want to compare them, you have to do something. You have to take one over to the other and then worry about that. And the other one is the 2 types are equal. And the reason why we want 2 types, this comparison, is precisely for what Severin was mentioning, that eventually types are going to be themselves points in a space. So that's a good reason. But also because we will see in a moment that types may depend on points. And because types may depend on points, we should be able to compare them. So types A and B are equal. And now, there are some rules for this equality, and they are the usual rules you're used to. Equality is an equivalence relation. You may substitute equals for equals. Right? If you see the S somewhere and you know that S is equal to T, you may replace S with T, and so on. So this all works as expected. Maybe a word of warning, you don't get to say that things aren't equal. You cannot say that things aren't equal because there is no logic. You cannot negate anything because there is no negation. We will have to learn how to negate things later. But right now, we only have equations. We don't have any inequalities. This is not as unusual as you might think, because we can look at algebra again. In universal algebra, what do they study in universal algebra? In universal algebra, you say, I study a certain kind of structure given by a bunch of operations and equations. And they don't say, and things that are not equations. They insist equations. So for instance, rings and groups are studied by universal algebra, but fields are not, because there are no axioms for fields that are expressible just in terms of equations. So yes, you limit yourself on purpose. You say, I'm going to limit my formalism, and this is going to be annoying because it doesn't allow me to say certain things, but there will be benefits. So for instance, in universal algebra, there are benefits. There are very powerful theorems of universal algebra that you can then use that tell you a lot about any kind of structure that you can describe this way. So it will be the same here. Anything that we can describe this way, we will know automatically that certain good things happen. So to just give you a preview, one thing that automatically happens is that anything that you construct in type theory, any kind of function you construct in type theory, is automatically continuous. So now, whether that is good or bad may depend on your point of view, but at least for certain people, it's a good thing. Right? You never, ever have to worry about checking that something is a continuous map. There is a price to pay. It's more difficult to do it. Right? So, okay. We have equations. Next thing we have is dependency. Now, this is a super important thing, dependency. And it is everywhere in mathematics. Dependency simply means this. Constructions depend on parameters. Even proposition 1 from Euclid does not just say construct equilateral triangle. It says construct an equilateral triangle depending on the segment that I give you. It's a dependent construction. I give you the segment, you give me the triangle on that segment. So it's a dependent construction. And this is something that happens everywhere, all the time in mathematics. For instance, you just say something innocent, like you say, consider, say, the space of continuous maps on the interval AB. This already is a dependent space, or what we would call, once we knew how to make this in type theory, a dependent type, because it depends on parameters. Right? Which space this is precisely depends on A and B. It's a little thing that goes unnoticed, but it is everywhere all the time. So, for instance, you say consider R to the n. You say consider you just say consider an n-dimensional manifold. That already in itself is dependent on n. Or in mechanics, you say consider a point moving in time. Well, that point is dependent on time. So this is something that happens all the time, and importantly, there are two kinds of dependency.
So that thing above doesn't depend on R?
Say again? No, because R here, it does not depend on R itself, because R is a fixed type, or a fixed space, right? We first, like we spend a year in the first year to construct R. Now we have R, it's that particular R, it's not something arbitrary. Whereas A and B are here considered to be arbitrary within the type R. So that's why they are parameters. Okay? Yeah? If I said consider CABR, where R is a topological field or some such thing, that's a parameter. Yeah. Okay, so two kinds of dependence in mathematics. A space may depend on parameters. And a point may depend. Or an element. They are of a slightly different nature, because here you have, in the first case, you have an entire space or an entire type changing as you change the parameter. Whereas in the second one, you have a point which is moving around as you change the parameter. So a picture would be like this. And this now should become this. I'm going to draw this picture over and over again. And this should be very familiar from the first part of the course. You have a parameter space, A. In it, as you move the parameter, you get a space which depends on the parameter. If I pick some other parameter y, I will get a different space b of y. Every point in the parameter space, so this is parameter space, and you can say for every point I get the dependent space. Yes? And is this familiar from the first part of the course? I sure hope so, because what am I talking about? I'm just talking about fibers. Right? Another way of saying this is that b of y is fiber, a fiber over y. We had lots and lots of fiber, fiber, fiber. In most cases, the fiber was always the same. So in the interesting cases, it was the same fiber over and over. But there is nothing that prevents us from, it could vary. It could be a different fiber depending on x and y. Yes? Okay, so that's another case. So in addition, our types may depend on parameters. And what happens then to dependent points? What's a dependent point? Well, a dependent point would be a point. Let me draw a slightly better picture here. So I think in many cases it's better to draw a one-dimensional parameter space. It's easier that way. And then up here, you just sort of draw something, some potato like that. Okay. And what you think of, the way you think of this is, given a parameter here, I have up here fiber or the space B of x. So for instance, over here, my B of x is very small. So say this is like y. B of y here is kind of small. Here it's fat, okay? Now, what is a dependent point? What does it mean that a point varies? Well, in the general case, to say that the point varies with parameter a means that for every value of the parameter, I have a point, let's say t of x. Here I don't have a lot of choice maybe, it's t of y, but in general, for every value of the parameter, I get the corresponding point. So pick a z here, you get here in the fiber bz some point sz. That's what a dependent point is. Okay, so do we know another name for this thing from homotopy theory? It's a section. So a dependent point is a section. And you can, in fact, connect all these and you will get section. I'm not very good at this. So far, nothing guarantees the continuity. I just like drawing continuous things. How are we going to write these things? Okay, so let's, yes? Yes, I switch between S and T randomly here, okay. And I think my pen is a bit too thick for this. So, T of Z, T is a section. Okay, so what we need some sort of a notation here, okay? So what was the notation in the first part of the course? In the first part of the course, the notation was this. You said B, A, P. This is how you said B is a space over A, and then you can look at the fibers, and the fibers change as you change the base point in the base. So now we're going to switch emphasis, and we're going to emphasize the fibers. We're always going to emphasize the fibers. We will be able to speak about the total space as well, but we'll start with the fibers. So we're going to say something, we're going to write it like this. X, A, B of X is a type. Okay, so the way you say, the way you read this is B of X is a type which depends on the parameter x from space A. And you can in general have more than one parameter, so the most general would be something like that. I have parameter x1, I have parameter x2, and then parameter x2 may depend on x1, like that, dot, dot, dot. It can get very hairy, and I'm not going to do this. I'm going to do this only once, just to show you what you could get. You could say I have n parameters, and then my x and my type B depends on all of them.
So this x1 to xn minus 1 in parentheses with an could be also some non-appearing.
This what I mean here is that this type here already may depend on the previous ones in the list.
So it
Yeah, it may depend on the previous ones. Yes.
But not on n, on some y.
On the what?
On y, which is not mentioned.
No, it must depend.
Yeah.
It may only depend on the things that came before. I want to make all dependencies very explicit. This is a bit unusual, and we're not often going to do this. But if you need to, sometimes you need to make all the dependencies completely explicit. And when you do, this is what we usually, in type theory, what people usually use. We're not going to use this a lot. But if I need to, I can say, I have a thing which depends precisely on these parameters, and so that's how I will write it. I write the list of parameters, then the funny symbol, and then the thing that depends. And so you could do the same for points. So for points, you could say, I have a point at t which depends, and so this is just now a fancy way of saying t is a section, right? It may be interesting to draw a picture. So what happens if I have this? Suppose I say x of type A, y of type B of x, c of type x, y is a type. What's the picture here? Well, the picture here is this. You first have A, and then B of x is a type which depends on A. So you pick your x, and here you have B of x. And now together you have C of xy. Right? Now you have to have something above, which is getting a little difficult to draw. Right? And so somewhere around here there is a fiber which would be the C of xy. So you get these iterated things like that, which is also something that is often considered in homotopy theory. You often are in a position to say, I have E going to B going to A, like that. It's not unusual to have these iterated fibrations. So that's what starts to happen. Okay, we should make a break. We have the basic ingredients. Unfortunately, today we will not be able to see any interesting dependent types. We are just going to practice ordinary types. But trust me, you were going to be sick of dependency already next lecture, because we do identity types. So we are just going to look at some basic types just to get a feel for how these things work. Okay, so in the next hour, let me give you an ambitious list of things to cover, which will not cover. I suspect we can't do this in its entirety, but doesn't matter, we'll just do it next week. I want the empty type, I want the 1-point type, the 2-point type, the natural numbers, I want products, I want sums, and I'd like to have the universe. It's a tall order for 45 minutes. But there is a certain method to the madness, so we may look at a couple of these, switch to the dependent types, and then do the rest of the basic ones next time, because I think it's important that you also see some of this dependency. Okay, so let's have a break now. Okay, Jaka will wander in eventually. He can live without the empty type and the unit type. So. Okay, so let's see. So now we're going to give postulates. I'm going to show you how you postulate a type. So it's a bit like explaining a new kind of space. That, you know, like how do you explain that you have a 1-point space? In an ambient, in a rich ambient where you, like set theory, the method is different. So the method is you sort of imagine yourself in this very rich universe of mathematics with lots of fruits to pick up, you know, lots and lots of sets everywhere. And then you find the sets that you like. You describe them, and it's like, these are the ones that I like. They're already there, right? So because of the axioms of set theory, because they generate this huge universe of things, and then inside this universe you can find all sorts of things that you like, and maybe some that you don't, but you concentrate on the ones that you like. That's certainly one point of view, and it's sort of this exploratory point of view of mathematics, where you think of mathematics as exploring what is out there. Type theory is a bit different. You think of mathematics as the activity of constructing things, of making them. And so we're going to postulate rules for making things. And so there is always a pattern when you describe a new type. So when you have a new type, there is a pattern that is, for good reasons, followed. And this is, you first give what is called formation. Formation explains how to make the new type. How to form the new type. You will see later on what this means when we have answer types. Okay, then you have constructors. How to construct points of this type. Then you have deconstructors. Deconstructors. How to deconstruct or use the points. So if somebody gives you a point of this type, what can you do with it? And then equations. And the equations are always about what happens if I construct and then deconstruct, or vice versa. What happens if I deconstruct and then I immediately construct? If I take the first and the second projection of a pair, like for instance, suppose I make a pair and then I take the first projection, what happens? There's an equation that explains. So that's the kind of equations that we want to have, okay? So let's try some. Let's try the unit type. Hi. We started without you. I was hypothesizing that you can actually live without the unit type, so it doesn't matter if you miss it. Okay, so the unit type, which I'm going to write as 1, and the idea is that this is a 1-point space. And now type theorists like to give these rules, postulate how things stand in terms of these fraction-looking things. And the way you read these fraction-looking things is like this. So somebody writes something like this, and then they put up here a bunch of things, and then down here something like this. This is called a rule of inference. And what this rule says, if you have these premises here, so if you've already constructed these things here, right, then you get to construct this thing down here. That's called the conclusion. Yes? Okay. So you will see through the usage what they are. But I'm going to write them like this. And today, maybe not all of them, whatever is most convenient, but sometimes they are the shortest way. So let me do that. Let me do it this way. Okay. So for instance, just to practice, so the formation rule. Well, the formation rule is just very simple. 1 is a type. You just say 1 is a type. Like that. And if you want to say unconditionally, you can put a line here and no premises. So this means you don't have to, there are no obligations, just 1 is a type. Okay? And now we have to give ourselves a point. So there's one constructor. And the constructor, we need some, Jaka, did you have a preferred notation for the point of a chosen 1-point space? What did you call it? Anything?
The asterisk.
Asterisk, fine with me. What did I use here? Lo and behold, I used the asterisk. Okay, so you just say there is a point called star of type 1. So this is a very simple, and now if I want to emphasize that this is now a postulate, put a line there saying no premises. So this is now saying we have a point. But with just these two, this is not enough. Because nowhere here did we say that this is the only point. Okay? So we're not now able to say that there is just one point. We so far know there is a point. So we need more. Okay? So as it turns out, what can you do if you have a point? If I give you the only point of 1, well, that's not very useful because it doesn't have any structure. You know that it's the only possible point. There's nothing to do with it. There are no deconstructors in this case. This is a bit of a strange case. Later on, we will see much more reasonable types. Are there any equations? Yes. The equations are the ones that are going to... How could we say, can we say in terms of equations that this space has at most one point? Because we already know it has at least one. How do you say it has at most one? We just say, well, any two points of this space are equal, right? So what you do is you say, okay, so suppose you have 2 points. Let's say S is a point in 1 and T is a point in 1. Then S equals T.
This is 1 and S is equal to
yes, so alternative. Alternative would be to say, if you have S of type 1, then S is equal to the asterisk. Both are possible and they're in fact equivalent. Like you can, if you have one, you get the other, because equality is an equivalence relation. So here, well, clearly you just stick asterisk for T to get the other one. But if you know that every S is equal to star, then every S equals to star, and every star equals to every T. By transitivity, you get S equals T. So there isn't necessarily just one way to give the equations. Yes?
I have a provocative question. If we have no logic, how can we express that this is an equivalence?
Okay, good question. How do you say without logic that equality is an equivalence relation? Well, you write more rules. Okay? So here are the rules for equality. And I'm just going to give you a flavor, say, for types. So for types, you would say things like A equal A, if A is a type. And if A equals B, B equals A. And if A equals B and B equals C, then A equals C. So you could say that this is a bit of logic, and you would be totally right. I mean, it's a formal system that allows me to derive equations, yes? But it isn't full-fledged logic in the sense of first-order logic, where it is sufficient to formalize directly the things that mathematicians say. Okay? It's not sufficient. It's just sufficient to reason equationally. It's sufficient for equations. Okay, let's try another one. Let's try the empty type. Now, the empty type is weird. So it's a bit of a misfortune that on one hand, I want to start with the simple types, with the simple spaces that are easy to understand, but on the other hand, they're not very typical in terms of how type theory works because they're weird. Okay, so let's see. Well, formation is, so now I'm just going to go down the line. Okay, so formation says, how do I make this type? And they'll just say, well, no, it's a type. 0 is a type. And then you say, what are its constructors? Does it have any points? No, well, so then we shouldn't give ourselves any constructors. Okay, but now, does that mean it's empty because we didn't give ourselves any constructors? That's not so clear. Maybe there will be some other magical way of constructing elements of this type, who knows? So now we need to say somehow that it's empty. And here we draw on category theory. Jaka explained what an initial object is in a category, and also a terminal one, but initial. So an initial object, how do you say that something is an initial object in a category? You say there is exactly one morphism from it to anything else. one way of saying that is what this says is it says it's as empty as any other object, right? That's what it says. The initial object is as empty as any other object, emptier, because it's more empty than any other object, because you can go from it to another object. So we do the same. We're going to say it's as empty as any other type, which means if I hypothesize that I have something of type 0, then from that I should be able to get something of any other type whatsoever. That will say this one is as empty as the others. So turn things around a little bit. Okay, so you say, okay, so suppose you somehow get an element of the empty type, and then you have some other type A. Then that should be enough. This is now the existence of the morphism from 0 to A, right? In terms of category theory, I'm now going to say there's a morphism from the 0 to A. Then there is a way to make a point in A. And now I need a notation here, and my ordinary mathematicians don't have a notation for this. I'll just make up one. I'll make up one that sometimes appears in books. I'll call this absurd. Absurd. Because the way you imagine this is to say, it's absurd to have E of type empty. There shouldn't be anything in empty. And so, because somebody says, I have something of type empty, now I can do whatever I like. It's an absurd situation. So I just get a point in any type whatsoever. I just get a point somewhere. Another thing that follows is that if somebody gives you something absurd like that, if somebody tells you, hey, let's imagine we have a point in a space that doesn't have any points. Well, okay, I get to construct points wherever I like, but I also get to prove whatever equations I want. So I should be able, so now I say, aha, okay, also, if I take any 2 points in any space, they'll just be equal at this point. Okay, so you want to say something like that. And that's the uniqueness part of the unique morphism from the initial object to right?
Only what follows from this equation for this is added to equations of the empty type.
Second?
This second judgment is also a number of equations for empty type, or did it just follow from?
No, these together axiomatize the empty type. I'm writing down things, I'm postulating them. I'm stating what holds.
So we also need the third one. The first two are not enough.
Sorry, we need
The first two are not enough.
the first two are not enough. The first two tell you, so the first two in principle would allow that there are several more, it's like a weak initial object. So the first two together give you a weak initial object, which means there's always going to be something going from 0 to A, but maybe it's not unique. But this will force it to be unique. Because you will, if I plug in here, absurd for one of these, and the other absurd for the other, they're equal. Yes. Homework, so exercise. I'll give exercises. So suppose you have a category C, and it has an initial object, say O, what is the slice CO like? What is that? Because that's like saying you're over the empty space. It can't be, it shouldn't be terribly interesting. Okay, so that's the empty type. It's super boring. Let's do something more interesting. Let's now switch to some dependent types because yes.
So is this A now a meta variable?
Well, to be okay. So I'm going to start taking shortcuts. If you're very paranoid, you say here A is a type. Yeah.
But the equations depend on this meta.
Okay, so first of all, you are a logician, and so you use words like meta variable, which don't mean anything in mathematics, but to say, yes, as far as this rule is concerned, A is a meta variable. Right? So what is your question?
Also, they're infinitely many.
instances. Well, of course, there are infinitely many instances of this, yes. For each type A, we get an instance of this. In fact, for each A, each S, and each T, and each E, we get one instance of this. Yes. It's like saying, it's exactly the same as saying, you know, A and B implies A, okay? So what does this mean? Well, it means that for A and B and A, you can stick in any logical statement, and then you will get an instance of it. That's what Niels. That's what Niels is asking. What is the status of A, B, and A? They're like schematic meta variables. It's exactly the kind of logic that I don't want to do in this course. Okay, I don't want to confuse anyone with logic. Logic is super confusing. I want to get over this and start doing mathematics as soon as possible. Okay, so let's do something interesting. Let's do the dependent sum. So the dependent sum looks like this. So I'm now going to describe the dependent sum, but I will stop. I don't know, do you want me to go on with these rules? I can go on with the rules. Let me try to describe it somewhat differently. Okay, so suppose you will tell me what's better. Suppose we have a type A and a dependent type Bx, which depends on xa. Okay? Then we can form a type called dependent sum. And it's written like this: sum xa. And now there are going to be a million different kinds of notation here. I will probably try to stick with this. But other notations that you will see are this. Would be a popular one. And okay, I'm not going to tell you what computer scientists write. They're totally nuts. Okay, so dependent type, and this is a type. What are its elements? So points of this thing are pairs ST, where, so I'm taking now pair to be a primitive construction. Pair here is a primitive construction. I'm declaring that there is a thing called pair, which is written like this, okay? And the conditions are that S has type A and T has type B of S. That was the constructor. There is one constructor called dependent type, dependent pair. Okay, what are some deconstructors? Given some point P of this type, there are the following points: pi 1 of P, which is of type A, and pi 2 of P, which is of type B, pi 1 of P. And these are called projections. Okay, it should be fairly clear so far what we're doing. Okay, we're going to draw a homotopy theoretic picture soon, but let me also write down the equations. Okay, what equations do we expect? Oh, here's one. What is the first projection of S and T? Oh, presumably S, okay. And then what is the second projection of S and T? Well, presumably T, but what space is this happening in? B of S. Yes. Okay, and there's a third one, which is what happens if I take the first projection. By the way, I will not be very religious about writing down parentheses. Okay, so I may start skipping parentheses. What is the first projection? I take the first projection of P I take the second projection of P and then I put them together, what do you expect will happen? Will I get back the same P? Well, yeah, that would be good. Okay, so this is, where is this happening? This is happening in sigma xa b of x p. Now, these two equations are just telling me that when I make a pair, the pair does not somehow magically forget its components, right? I can still get the components back by pi 1 and pi 2. They are not gone. Right? So when does it happen that you have an operation which forgets its arguments? Addition is like that. I say 3 plus 5. Okay, I get 8. Is there some way to now magically reconstruct how I got the 8? No, because there are many ways to get 8. But the first two equations are saying, no, no, no. When you make a pair, you're not forgetting the first and the second component. You're not sort of welding them together in some way so that you will never be able to figure out what they were initially. So that's what these are saying, right? They're saying, given a pair, you can actually look inside and get S out. And this one is saying something interesting. This one is saying everything's a pair. This is our way of saying that, see, in principle, it might happen that apart from this way of making points, so this says pairs are points of this type. But maybe somehow magically there are some other points of this type. I don't know, maybe later on I will give myself some other rules, and then because of those other rules there will be some strange way of creating new elements of this type. No, this equation says once and for all, if you have a P of this type, it equals a pair. Which pair? Well, this pair. What's the picture here? What did we just describe? Did we describe a familiar notion from homotopy theory? We have A. We have the dependent type, B. Here's B of x. As I move around, B of x changes. What is the sum? Where is the sum? What is the sum? It looks like the total space, right? So when I create the total space, ugly total space, there, it goes sort of veering a bit off on the right here, okay? So I sum them all up. So what are the elements? I take an S here, and here I get B of S. In here I find the T. And so my space consists of all such pairs. So what would be a good picture of this total space? Well, it's something that looks a lot like this, because it's just this potato, right? The only thing you should not, the only difference to point out is this. If I just say T, then I'm thinking of T as an element of the fiber. But if I say the pair ST, then I'm thinking of the space of the point in the total space. There is a difference between a point of the total space versus a point in the fiber. This is where we were emphasizing earlier, every point lives in exactly one space. So this T here lives in the fiber ST, B of S. But the pair ST will live in the total space. So the good picture of the total space is to just simply be brave and take, well, not that brave, that's an eraser. Okay, so this is the total space. All of this together, where you have to keep in mind that when we are speaking of the elements, we are thinking of pairs. You always need to make a pair so that you can see what fiber it came from. So the total space. There should be a nagging question here for you. And by the way, where is pi 1 now? That's pi 1. So we are, in a way, when you have a dependent sum, that's the super nice situation where your total space is already presented in this way, where you simply take the first projection to get down to the base. So it's a particularly nice case of a fibration where your total space has a super nice form. And now you should go back to homotopy theory and say, hey, isn't every fibration of equivalent to one of that form? And the answer should be yes. Easily, in fact. Right? So that's something to think about. Okay, that's the total space. One nagging question should be this. If you think of this very set theoretically, then you might think that we constructed a disjoint sum of fibers. But we did not construct the disjoint sum of fibers because the total space is not a discrete sum of fibers. The total space typically has a very interesting topology. The fibers are nicely glued together to form some interesting topologies. As I move, I can move continuously in the horizontal direction from one fiber to another. So something mysterious is going on here because it looks like, it looks as if I formed the total space out of the fibers, but I never explained what the topology of the total space is supposed to be. So some magic is going on here. And this magic will take some getting used to. It just so happens that this formalism, by the time you have already, when you explain what these fibers are, at that point, you will already have determined how the fibers fit together. That's what's going to go on. Our notion, our ways of defining fibers, that is to say dependent types, will always implicitly carry with them information on what happens when you put it together into a total space. A good example to discuss, which we shall discuss, is, for example, the difference between the double cover of the circle and the trivial double cover of the circle. Because there it looks like we have a space which depends on the circle, and the fibers are always just the 2-point space. But something else, something different, something happens globally. And so we will see how this affects the definitions. So that, keep in mind when we get there, we will explain this mystery. Okay, so another construction which is fundamental is the dependent product. Okay, so how does that work? So now once again, given a type A and a dependent type, now allow me to write it like this, it's shorter. Okay, given a type and B which depends on A, we can form the dependent product and write it like this. Now I have to explain what's in it. So the idea is that this is the space, let me see what is the idea, the space of sections. That's what it's supposed to be. So one element should be a section. You don't directly see this space in classical treatments of homotopy theory, although I suppose it's not unheard of. It's something that you would use if you had some use for it. You wouldn't think it's totally weird. It just doesn't play, I think, as central a role as it is going to play here, because this is going to be a central construction. But you can certainly recognize lots of constructions as being about this space. Without a doubt, sections are an important thing. Yes. Yeah. So here, what are the elements? Okay. So now we want to say that the elements are functions. Aha. But now we need to do something. Okay. So we do it like this. If we have a dependent point, right? That's what we need. If we have a dependent point, Okay, so what does this mean? This means that t is going to be speaking very concretely, this is going to mean that t is some expression which depends on x, right? Yeah. In practice, when you write down actual dependent points, you will write down something which depends on x here. Okay? If this is a dependent point, well, what does this mean? This just means that if we go back to the previous picture, or just this picture here, which means wherever I look, I have a point. Wherever I look, I have a point. Well, but then I have a section. Okay? So I just need to package this up. So I need some way of packaging this up. This, I need to package it up. So I'll package it up in the traditional notation, then explain the same notation. Then you write it like this: lambda xa t of x is some point of type pi xa p of x. I apologize in the name of all logicians, and in particular my academic grandfather who invented this notation. It's called the Lambda Abstraction. And this here, it used to be just a small corner of logic, but nowadays functional programmers use this all over the place. So it's going to take over the world eventually. So what this means is it's nothing other than just saying x maps to t of x, where x ranges over a. Okay. It's just a way of writing down a function which takes x to t of x. It's precisely what it is. It's just a way of packaging things up. I don't think we will need this too often, but that's how it's written. It's a section. It's called a section. Okay, so what are some equations? Oh, what can we do with functions? What is it that we can do with a function? Okay, so given, say, some. Now it's traditional to use the symbol f for elements of this, or because they're functions. Pi x a b of x and some point t in a, we get, well, what can you do? You can say f of a, and so that will land you where? Oh, sorry. T. I'm just describing functions, really. The only thing that is a little slightly weird is that the domain depends on the codomain depends on the domain. Where exactly you land depends on the argument. The type of the result depends on the argument, not just the value. That's the only thing that's happening. Other than that, it's just functions as usual. Okay, there are some equations. These are so basic and so ingrained into mathematicians' knowledge that they don't even notice them, but let's write them down. Okay, the first equation says, if you have a function and you apply it to some argument, how do you calculate the thing? Well, you stick the argument inside the definition of the function. That's all you do, right? Like if I ask you, I have a function which takes x to t of x. What will happen when I apply it to some s? What will happen? Well, you're going to get t of s. Okay? But what this means, replace x with s. Right? That's how you should read this. It's nothing new. You do this in your dreams. Okay? It's always there. Okay? There's another equation. It's important. I'm going to present, there is a weak version of it and a strong version of it. If I show you the weak version, you're going to be confused. I'm going to show you the strong version. I'm simplifying things a little bit, but this one makes a lot more sense, okay? And it's the strong version. Let's see, how do I want to phrase this? No, let's not do the strong version. Let's do the simple version. Okay, so the simple version is this, because it still follows a certain pattern. Suppose I have a function f, and I apply it to x, and then I immediately make a function out of it. So I say, consider the function which takes x to f of x. Well, that's just f. Okay. So these are the kind of trivialities that one has to notice if one wants to do foundations of mathematics. But there it is. Right?
There might be some confusion.
Where?
So this f was originally an element of pi type, right? Whereas
Aha.
t.
Let's see where. Okay, let's write down the types.
t
F came from here. F came from here. T, this T here, is dependent on A. Yeah? It's an expression that actually contains X.
So, but because notation looks the same.
Sorry?
Notation looks the same.
Which notation?
This long
Oh, yeah. Okay, that's a bit unfortunate, yeah. If we were super careful, we would for this, we would need a different notation than for that. But we don't. I really don't want to do that. I want to have one lecture of this logic stuff, and then next time I want to do mathematics, if at all possible. Okay, so that's the space of sections. It's difficult to draw the space of sections because it's going to be quite infinitely dimensional in most interesting cases, you know. Like, how do you draw the space of all functions from natural numbers to natural numbers? Well, you can, but it's not nice. Sorry. It's easier to just think of it as seeing one element at a time, namely one section at a time. Okay, there are some important special cases. And we get the special cases when we apply the above constructions to the trivial case when you have a type which is constant. So you can have a type which depends on another type, but in a constant way. So it doesn't really depend. Okay? Like this. Suppose we have types A and B. Okay? And now define a dependent type. B, which depends on X, by saying, well, this is just always, sorry, not B, the other one, this one needs to be something else. C, call it C, which is just always B. What did I just do in terms of fibrations and spaces? Well, in terms of fibrations and spaces, I created the trivial fibration. Here's A. Here's B. Not quite. I can make it look better. Okay. Here's B. Where's C? Well, C is just going to have always the same fiber. So it's going to be just a rectangle like that. That's not actually C. C is a dependent type, which at every x gives me B. At every x, at every point, keeps giving B. What is this rectangle properly speaking now? That's the total space, so the dependent sum. So then, the sum xa c of x is just a binary product, the binary product, right? Is a special thing. It's called of A and B. And so we see that we can get ordinary products this way. So we can say A cross B, by definition, is the dependent sum where x of xa B. See, no dependence here. It's always the same fixed B. And then we're going to get just the product. And what will be the elements? Well, the elements will be the ordinary pairs, where you take one component from A, the other component from B. So ordinary product of two spaces or ordinary product of two types is a special case of dependent sum. Let's do the same thing for pi. So what is a pi? What's a section of this rectangle?
We could also
Yeah.
represent a binary product with the product before.
With a pi?
Yes.
Yes, we can also present the binary product with a pi, but first we need a two-point space. Yes. So if you have a two-point space, then let's say suppose it contains the points 0 and 1. You make the dependent type 0 goes to A, 1 goes to B, and then you form the product, and you will again get A cross B.
But then it's a different thing.
Well, eventually we will be able to show that they are equivalent types, and therefore by univalence equal types in the universe. There will be a path between them.
But there was a different construction.
Okay, so yes, they will not be the same type, they will be equivalent types. Yeah. Okay, so what do we get if we calculate the pi of this? Well then, what is a section of a trivial vibration like that? It's just the same thing as a function from A to B, because at every point in X you pick a point in B, so it's a section. Okay, so then we have similarly if we form A, so I will write it like this, A arrow B, and another notation will be also B to the A. Both, I might use both, but I think I'll prefer the first one. This is just pi XAB. And these are just functions, maps, from A to B. Okay. Now we don't actually know. We don't really actually. If I ask you, well, okay, but which functions can you define from A to B? What, like, how do you even get a function? Well, so far you only have one way of doing it, which is you write down one of these lambdas. So, for instance, you surely can write down some functions. For instance, can you write down a function which goes from A cross B to B cross A? Sure. Okay. Lambda. I take P. P lives in here. Okay. How do I make an element here? It's a pair. The first component has to be from B. Can I get something from B? Sure. Pi 2 of B. Can I get something from the second one? Sure. Pi 1. So we have sort of we have the bureaucracy to create all these bureaucratic functions. But we neither have any interesting spaces like spheres and circles, nor do we, or real numbers, we don't know about that yet, nor do we have natural numbers yet. So we just have a lot of bureaucracy at this point. So we need to do more. Okay, so let me just quickly end with the last idea, which I think is illuminating, and that's the universe. Just because I want to show you how it simplifies things, okay? So, you know from set theory that you need to be kind of careful about the set of all sets, because otherwise you get into trouble. So, the first version of Martin Löw's type theory had type in type, and he got into trouble. So, you can have, the idea is this, aren't types constructions? I mean, look, when I was describing types here, I was giving you ways of constructing types. So types themselves are constructed, but if they're constructed, there should be the type of type constructions. So there should be a type of types. Except that you hit the usual paradoxes of self-reference if you say that there is a type of all types, but you can say that there is a type of all small types. Okay, so certain types, so there is a type U, which contains as its points. Which types? Well, the small types. By that I mean 0, 1, 2, natural numbers, and then the sum of small types and the pi provided A is already in U and B of x is in U for every x in A. So there's a type which you get by closing up. It contains, so it's kind of like a type of all types, but it doesn't contain itself. It just contains the things you can get out of these people here. And so we call it the universe. And now you can actually have another universe. So that U becomes an element of U prime, and then this U prime also contains all the other stuff. And then you can keep going if you want to. And then you get sort of a sequence. And we won't really need that. We will mostly speak about just one universe, and maybe sometimes two. But it's good to have this idea of one universe, in particular because of this, and this is important. A dependent type B with parameters xa is just a point of the function space A to U. Okay, that's the important bit. Which simplifies a lot our treatment of what's going on, because now we get to treat types as points in the universe, and lots of interesting things happen. For instance, you can ask, what is the homotopy structure of U? That should be an obvious question to ask. And the answer is very, very interesting. And then you can ask, okay, you can simplify things by, you don't have to speak about these parameters and stuff. You can just say, well, it's just a map into the universe of types. So a very similar device works in set theory, where for U, you would just take the class of all sets. And then you can speak about functions from a set to a class, and there's no problem. You can do everything you like that way. So here you can think of U as some sort of a supertype, which accomplishes a similar idea. And so we were going to discuss this also. The universe will come up. But it's at first, in the first instance, it's a simplifying idea. In the first instance, you see now that dependency is just this. From a homotopy theoretic point of view, this looks curious because it says that there is a classifier for all fibers, right? Okay, I'm going to give something just for the experts in the room. What this is saying is this. Every fibration appears as the pullback of a universal one. Which is true. So you know how to describe this thing here?
I mean, well, the universe is not, there isn't a single universe.
Okay,
right?
so what you are familiar with is a smaller universe that is going to take care of all fibrations with a given fixed fiber, right? For example, okay? Now, I'm much more insane, right? I want them all.
Is all the
Yeah. Yeah, I live dangerously. But it's useful to have the classifying, right? For a fixed fiber, there's lots and lots of useful things that you can do, right? Imagine the things you could do if you had one that classified them all. It's like the Lord of the Rings. right? So we want that sort of thing. Okay, let's stop here.